Right, let's dive straight into this explainer by treating your Cambridge physics exam exactly like a high-stakes trading floor. Think about it. In the world of high finance, every single trade, every tiny fraction of a cent is an investment that has to be tracked with absolute precision. Well, in physics, every measurement you take is your investment. And just like a dollar amount means literally nothing without knowing the currency, in physics, a number without a unit and a stated uncertainty is completely meaningless. You're just throwing points away. Today, we're going to master the exact strategies you need to safeguard your data and maximize your marks when dealing with physical quantities and units. Let's get into it.
So here is your physics success blueprint for today. We'll cover 5 key areas: the measurement challenge, precision versus accuracy, systematic and random errors, choosing the right instrument, and finally, combining your uncertainties.
Okay, Section 1, the measurement challenge. We really need to talk about why perfect readings simply do not exist.
I absolutely love this concept because it completely shatters a common myth. Listen, having an uncertainty doesn't mean you messed up. It just represents the total range of values within which your true measurement is likely to lie. For instance, think about a metal meter rule. It literally expands as the temperature in the room rises. So at only one specific temperature will the scale on that ruler be perfectly precise. At literally any other temperature, you have a built-in uncertainty just because the metal expanded. You didn't make a mistake, the universe just has variables. It's that simple.
Moving on to Section 2, precision versus accuracy. We are decoding the two most confused terms in all of physics.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's talk precision. Think of precision as the tight clustering of your data points. If you measure the current in a wire 10 times and you get 2.01 amps, 2.02 amps, and 2.00 amps, you have fantastic precision. The smaller the range between your repeated readings, the better your precision. But, and this is huge, it has absolutely nothing to do with whether those readings are actually correct.
And this brilliantly illustrates the trap so many students fall into during exams. You can have highly precise readings grouped super tightly together, but if your instrument is fundamentally flawed, those readings won't be anywhere near the accurate true value. Imagine using a highly precise micrometer screw gauge that reads to the nearest 1/100th of a millimeter. Your precision? Incredible. But if that gauge has a massive zero error and actually starts reading at 2 millimeters instead of 0, well, your incredibly precise readings are entirely inaccurate.
Let's roll into Section 3, systematic and random errors. This is all about protecting your data on the exam.
A systematic error is honestly like a bad recurring trade. It shifts all your readings consistently above or below the true value. Because it happens by a fixed amount and in the exact same direction every single time, you absolutely cannot fix it just by taking more readings and averaging them out. The average will just be equally wrong.
By comparing these two directly, we see a massive difference in how we handle them. Systematic errors require you to actively change your technique or physically check your zero readings. Random errors, on the other hand, are much more forgiving. Sure, they scatter your readings all over the place unpredictably, but because they are purely random, they can be mitigated mathematically. By taking multiple readings, finding an average, or plotting a graph and drawing a beautiful line of best fit, you can dramatically reduce the impact of random error and instantly improve your precision.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, if you want to protect your accuracy, watch out for these systematic pitfalls. A classic exam scenario is the worn end of a meter rule. If the wooden end is chipped, pushing it against an object means you aren't starting at true zero. The pro strategy to fix this? Never place the worn zero end directly against the object. Instead, start further down the rule, say at the 10-centimeter mark. Take readings at both ends and subtract them. Boom! You've just eliminated a systematic error with superior technique. You also have to consider your own reaction time. If you're manually timing a pendulum swing, your human delay in pressing the stopwatch is a systematic error. You reduce that impact by timing 10 swings instead of just 1, making your reaction time totally insignificant to the total.
Conversely, these random errors destroy your precision. Reading a scale from slightly different angles each time introduces variable parallax error. But, and this really shows the pure ingenuity of experimental physics, you can entirely eliminate parallax error by simply placing a mirror behind the instrument scale. When you look at the scale, if the physical needle completely covers its reflection in the mirror, you know for a fact you are looking at it perfectly straight on. It's a brilliant little trick.
Section 4. Choosing the right instrument. We need to make sure we're matching the tool to the task.
Knowing the theory is great, but applying it means choosing the absolute correct instrument for the specific exam question in front of you. Look, if you need to measure the diameter of a tiny steel sphere or a strand of human hair, a standard meter rule's 1 millimeter uncertainty is completely useless. The hair itself is thinner than the uncertainty. You must upgrade to a micrometer screw gauge. You place the object between the faces and tighten the ratchet until it slips. This lets you read to the nearest 1/100th of a millimeter, shrinking your absolute uncertainty to practically nothing.
This cheat sheet right here perfectly anchors the theory to tangible lab equipment. It shows you the exact built-in uncertainties you've got to account for. Notice that a stopwatch with 0.1 second divisions has an absolute uncertainty of plus or minus 0.1 seconds. An ammeter with 0.1 amp divisions gives an uncertainty of plus or minus 0.1 amps. Just a quick tip, for digital meters, manufacturers often quote uncertainty as a percentage plus a few digits, so always double-check the scale you're using.
Okay, pay attention, because this is a massive trap that catches so many students out. Let's say you measure the position of a lens at 95.2 centimeters. Then you move it to 93.7 centimeters. The difference is a tiny 1.5 centimeters. But here's the catch. Each measurement with a meter rule has a plus or minus 0.5 millimeter uncertainty at the zero end and another 0.5 millimeters at the reading end. That is a full 1 millimeter of uncertainty per measurement. Because you took two measurements, those tiny uncertainties combined to 2 millimeters. 2 millimeters out of a tiny 15 millimeter distance moved? That compounds into an absolutely unacceptable 13% error. If you hit this in an exam or a lab, it's a huge red flag. It means you must completely redesign your experiment to measure larger differences.
And that leads us perfectly into Section 5, combining your uncertainties. Let's tackle the mathematical final boss.
You'll rarely just measure one thing. You'll measure several variables and smash them together into a formula. So how does uncertainty travel through that math? Well, here are your mathematical cheat codes. If your formula asks you to add or subtract two measurements, like finding a change in temperature, you simply add their absolute uncertainties together. Easy. But if your formula requires you to multiply or divide quantities, you cannot add the absolute uncertainties. No way. You must first convert them to fractional or percentage uncertainties and add those together. Oh, and if a quantity is raised to a power in your formula, just multiply its percentage uncertainty by that power.
Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Let's look at how this builds into a final calculation. Say you're calculating the volume of a cylinder using a measured diameter and length. Let's say the diameter has a 4.0% uncertainty, and the length has a 1.3% uncertainty. Because the formula for the volume of a cylinder uses the diameter squared, that diameter's 4.0% uncertainty must be multiplied by 2. That gives us 8%. Add the length's 1.3% and we yield a total percentage uncertainty of 9.3% for the final volume. See? Not so scary when you know the rules.
All right, I want to leave you with this final puzzle to test your new mastery. Trying to measure the thickness of a single page of a textbook directly with a ruler, or even a micrometer, will give you a massive percentage error because the absolute uncertainty is so close to the actual measurement itself. So, using the exact rules we've discussed today, how could you measure it to drop your uncertainty down to a totally acceptable 0.05%? Hint, you are going to need a lot more than one page. And you'll need to think about how dividing by a pure number affects fractional uncertainty. Figure that out and you are 100% ready for the exam. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.